Hello, I'm Ece Demir. Today I'll be doing my presentation on the paper titled Application of Multi-Objective Genetic Algorithm for Optimal Combination of Resources to Achieve Sustainable Agriculture based on WEF Nexus Framework by Karamian. Here you can see the table of content for my presentation. And here you can see the outline of the paper for easier navigation during this classwork. Let's start with introduction. In order to deal with global challenges on water, energy, and food security, the WEF Nexus concept has emerged as a solution. The WEF Nexus is considered to be a complete concept for achieving sustainable development by identifying connections and synergies. The improper use of water and energy for agriculture has a serious impact on food security, particularly in developing countries. As a result, WEF is closely tied to irrigated agricultural systems. This paper outlines a model based on multi-objective genetic algorithm that conceptualizes balancing the goals of sustainable agricultural development, highlighting the impact of interactions between social variables and WEF Nexus index in agriculture. Here you can see the decision-making framework of the proposed approach. Firstly, the objective function inputs are determined. Then genetic algorithm is used to find the optimal solution with respect to three objective functions. Let's move on to the materials and methods in the study. The study area here is Kermanmash province in Western Iran. In this study, the predominant crops in the area are wheat, barley, maize grain, tomato, potato, and rapeseed. The main issues in the area are the poor management, the lack of supervision, the unauthorized abstraction of groundwater resources, and improper use of water and energy resources. This study involved 4 steps. The first one is calculating the WEF Nexus index. Where to calculate it, you have to find 6 sub-indicators, which were normalized and weighed to determine the final one. The second step is the assessing of environmental impact of crop production, where LCA was used. The pollutants were first measured and then multiplied with the pollutant emission factor and then classified into 7 categories of impacts. And then the final index was determined through normalization and weighing. In the third step, assessing the social dimension of sustainable agriculture, where various studies were reviewed and experts were interviewed to find 13 variables and 5 categories for them. In the fourth step, we determined the optimal cultivation pattern using multi-objective genetic algorithm, MOGA. The MOGA used in the study was CW3, which had a better convergence rate than the traditional model. The results of this CW3 was presented as Pareto plot. Here you can see the input parameters in the research framework for each objective function. The important ones here are the water, energy, and food nexus index sub-indicators, such as water consumption, energy consumption, productivity indicators. Now, the objective functions include maximizing the WEF Nexus index, minimizing the LCA impacts, and maximizing the social dimension of the agricultural sector while being limited by constraints. Here you can see that all of them are written to be minimizations, but the ones that you need to maximize, they're written as reciprocal. There is also in the first objective function, available water penalty term, which you can see here. Let's move on to the constraints now. The first constraint is the percentage of area under cultivation of dominant crops in the studied area. Based on this condition, the percentage of total area has to be equal to 1. The second constraint is for the total area under cultivation of crops, because there is 10,000 hectares of area available only. The third constraint is on the available water per hectare. WE is the available is the water you use. WA is the available water per hectare. There is surface water and groundwater involved in the available hectare variable. Now there's the model solution, which has been done using the compromise programming. This method is commonly used to help to find the best solutions in the Pareto front. The general equation for it has been given here. Now let's discuss data collection and processing. The WEF Nexus index includes 6 indicators, which you can see here, and the first of them, which is water consumption, uses meteorological data, and the other 5 indicators were obtained. The data for it was obtained through questionnaire and interview data with 3,015 farmers. 315. The LCA here again uses the data from the questionnaire, and it also has the inputs of diesel fuel, water, electricity, chemical fertilizers, and poison. Social dimension here uses 13 social variables, 5 categories for them, and the data was obtained from questionnaires and interviews. Let's move on to the data processing step. The Water consumption for crops were determined using CropWatt, and the input for energy was determined through the questionnaires. The inputted data was multiplied then with the energy equivalents. There's additional productivity indicators which were calculated through experimental formulas in our study. Here you can see the productivity indicators, and here you can see the social indicators. As you know, there's the LCA conducted here. So firstly, in the LCA, the functional unit is chosen to be 1 hectare, and the system boundary is chosen to be farm gate. In the second step of the LCA, all inputs and outputs are measured, and the amount of gas emitted from each of these were found by multiplying the inputs and outputs with the emission factors. And then in the third step, potential effects were assessed by multiplying the gas emissions with the impact factor of the related category. And here you can see the LCA final index formula. Now let's move on to the results. Firstly, we will view the results of the WEF Nexus, LCA, and the social indicators per hectare. These have to be obtained for the optimization model. Here in the figure 4, the WEF Nexus index results were depicted. In the first one, the water consumption, so the blue water consumption is determined to be high, accounting for 70% of the water of different crops. And in the B, which is the energy consumption, potato is determined to be the most energy consumptive crop in the area. And the reason for the most water consumption has been determined to be water. In C, which is the productivity indicators, are shown here, and the tomato has the highest values. And D gives the WEF Nexus index values for all crops. In here, maize, rapeseed, wheat, and barley have the low values, while potato and tomato have higher values. So tomato is the most stable crop in the WEF Nexus index. We want the WEF Nexus index values to be high. That's the objective. In figure 5, you can see the environmental impact of agriculture sector in terms of different crops per hectare. In the last one, you can see the LCA final indicator. And in the region, maize grain have the highest environmental impact according to this picture. Now, figure 6 displays the social dimension status of each crop based on 5 categories. According to this, desirability of working conditions is the highest priority for farmers, while participation and communication is the lowest priority. Now let's move on to the genetic algorithm solutions. Multiple iterations were done in the algorithm to attain optimal values of the study parameters and validate the model. Table 4 here and figure 7 here show the optimal values of the initial parameters based on the experiences gained from different iterations and trial and error. The convergence of the algorithm occurred in the 5th step with 300 iterations and an initial population of 50. To choose an optimal cultivation method, the results of each 50 solutions obtained from the last iteration of the algorithm were examined. Based on compromise programming, 2 scenarios were investigated: minimum CP and maximum CP. Minimum CP is the ideal selection that you want here, since our objective is to minimize. However, the evaluated maximum CP is also kept and evaluated for the sake of comparison. Here in table 5, you can see the current and optimal crop patterns in the study area. Selecting the maximum CP, which gives you the minimum WEF Nexus index, maximum LCA impacts, and minimum social dimension, results in a significant decrease in the area for wheat cultivation, removing it from the cultivation pattern. And in addition to this, the area under tomato cultivation increases with the minimum CP pattern. Now, in here, table 6 presents the WEF Nexus indicators values over the entire area currently in minimum CP and maximum CP. Table 7 shows the summed up indicator values over the entire area. It can be seen that selecting the maximum CP pattern increases the water consumption and energy consumption. However, when selecting the minimum CP pattern, water consumption is reduced by 2.56% and energy is saved by 12.71%. Now here, table 8 compares the impact categories of current and optimal cultivation patterns using LCA. In table 9, the total pollutants in the study area decreased in the minimum CP and increased in the maximum CP pattern. Table 10 here displays the social dimension categories for current and optimal crop patterns. In the minimum CP pattern, all categories socially have increased. Let's move on to the discussion. Average of social benefits increase in the minimum CP scenario, while the proposed model saves water and energy in the minimum CP. The findings indicate that instability in agriculture and resource management are caused by resource mismanagement in the study area with lower values of WEF nexus index. India government offers high amounts of subsidies to farmers growing wheat, and as a result, unreasonably, this system reduces the area because the environmental impact of wheat is way too high because pesticides and other inputs are subsidized by the government. And the model tells us that the wheat should be reduced as a production because it has high environmental impact. However, by stakeholders, this is an unacceptable option because they are producing it with high subsidies. So the study found that balancing economic benefits, environmental impacts, and social benefits was possible, but required changes in the crop cultivation patterns and considerations of uncertainties. The study's modeling framework is adaptable, but needs further research regarding the extending of measure of important variables in different human ecologies. Thank you for listening. If you have any questions, I'll be happy to answer. Here's my only reference.